All right, so today I'm going to go through the sort of remaining enolate chemistry. So we'll discuss enol chemistry a little bit, and then we'll discuss some alternative reactions that I'll show you that are very enolate-like in terms of mechanism, and so show you guys that there's a lot of other compounds that you could imagine reacting in a sort of a similar way. See how much time that takes, and if we have additional time, then we'll start getting into dienes. And I anticipate that we will have a little bit of time to go into dienes. But a couple classes ago, but we'll start with enamines. So a couple classes ago, we began to discuss the sort of comparisons between enolates reacting and enamines reacting. If you guys can remember, again, if we think about the enolate, what we're talking about, right, is a compound that will often draw in this way, but we'll think about it reacting in the other sort of resonance form, right? There's this carbon-based nucleophile that we often think of, and again, and that's going to attack one of those several different electrophiles that we had in mind to sort of make that bond. And then we also mentioned how sometimes if you have an enamine, right, you could draw similar resonance forms that shows the reactivity of these. In this case, it will be sort of zwitterionic, at least in nature. So we'll split the dipole. And again, this is just the resonance form that's going to sort of show how this would work. And again, these can react with electrophile. But again, one of the differences, as you'll notice, right, is that the leftover product, the remaining product after it reacts with that electrophile, right, has the ammonium here. And so oftentimes the product after the workup of a reaction like this is sometimes, for example, a ketone. Sometimes you can imagine it enolizing and you'll regenerate the enol. And so depending upon how you work this reaction up, you could imagine situations where in the presence of water, you can imagine situations where you'll get to the ketone, or you can imagine situations where perhaps you just have a milder base, for example. Right, so for example, you run this with a mild base, maybe you'll get back to, as you might imagine, through a mechanism, sort of regenerate the sort of enol, and so you guys should sort of be able to see that. It turns out I don't generally, like, enol chemistry isn't something, it's certainly used quite frequently, but in most cases, I think when we're starting to think about synthesis or when we're starting to think about the reactions of these molecules, much of the chemistry that we're discussing, right, in terms of making these bonds with the alpha carbons, I think in general, you can simply deprotonate them and they can work. And so there can be advantages, but I think for the sake of organic 2, sophomore organic 2, whatever you want to call this course, you can sort of use either one of these. But what I really wanted to do with enolate or enamines is kind of tell you guys how I think of them as being valuable, at least for synthetic chemists, because if you look through the literature, it's rare that people will make the enamines simply to carry out reactions. Where you see it mostly, and we alluded to this probably a week and a half ago, is in asymmetric catalysis. Okay, so asymmetric catalysis is basically the process by which you generate chirality of a molecule as a specific enantiomers in a catalytic way. And so if you start with something that's achiral and you make a bond, and by making that bond you create something that's chiral, without anything sort of exogenous being added to the reaction, right, you're going to get a racemic mixture, right? So in general, if you take, say, for example, a ketone, right, and you take this molecule and you treat it with LDA, and then say, for example, an aldehyde, right? We're going to make, so this is achiral, this is achiral, but when this reaction takes place, right, we're going to generate a stereogenic center here, right? So, and at that stereogenic center, we have sort of the two possibilities. It could be sort of R or S. But as you guys might remember from discussions on chirality, one of the big reasons why organic chemistry in this course is so important for people that are, say, for example, going to medicine or so forth, it's because chirality is so important to a lot of physiological conditions, right? We are chiral, right? Proteins, nucleic acids, many of the other molecules, whether it's hormones or whatever, these are molecules that have chirality and they react with other chiral molecules, and there are selectivity issues that are associated with that are important. So you guys have probably all heard the stories of drugs that have, say, for example, 2 enantiomers, and one does something great and the other one does something bad. And so there's this important selectivity issue that comes in, and it's important as synthetic chemists that we address chirality, and so it's important that we can make and run chemistry where perhaps we can make one single enantiomer. And so without anything sort of exogenously administered, you're going to get this mixture, racemic. Drawing this in terms of plus minus because we'll get both enantiomers. But enamine catalysis is one of the things that's really opened up, I think, asymmetric synthesis. And it's part because derivatives, for example, we start to look at and think about how we make enamines, right? We make them with secondary amines, right? And so we take these molecules and treat them with secondary amines. Right? And we condense them. This is oftentimes how we get to enamines, right? And then if you did this, as it turns out, and we might have discussed this previously, but proline, right, is one amino acid, which has stereochemistry to it. Right? And so now you can imagine a system where you have something where this is now your nucleophile. We can imagine a couple different things taking place here, right? So if I just redraw this and start thinking about the approach, we can imagine a couple different mechanisms by which this molecule could instill chirality. I'm not going to go into the specifics of this. This is in the course on asymmetric catalysis, but I'll just tell you in some instances where you have proline, you'll notice that, for example, there's a carboxylic acid here. You can imagine that carboxylic acid, say, for example, activating, say, for example, the carbonyl. So I'm going to draw a terrible transition state here, but just to show that you could have this hydrogen bonding, right, which will effectively direct, this is called the directing group effect. The proton will activate the carbonyl, and this will direct, say, for example, from a single face to generate that enolate. You could also imagine a steric effect, right? If instead of it being a carboxylic acid, other people have done plenty of chemistry where instead of having directing effects, you can have steric effects. But then again, even thinking about proline or proline derivatives, people have made molecules where they, say, for example, add phenyl grignard. This is something that a guy at Princeton did a lot of work on, David Millen. You'll basically have this huge bulky group here. So you can imagine taking proline, right, and treating it to a couple equivalents of Grignard, right? It'll add in twice, or take ethyl ester, for example, add a couple equivalents of Grignard, and then to make it even better, they soup up the alcohol that's generated with TBS, and now you have this molecule, and it would be different, right? Because what would happen in this case is that you've got this huge group that's, say, for example, blocking one face that enolate, right? And so now the approach is going to come from the other way. And so when I think of enamine chemistry, I think one of the biggest things to me is sort of asymmetric catalysis. Now, people, I think, asked when we discussed this briefly before, well, what about the iminium, right? What, you guys are showing, I'm showing you guys here how say, for example, how the nucleophile is the chiral component, right? But what about if the electrophile is the chiral component? Certainly there are instances where you could do that as well. But it turns out the key word here is catalysis. And as it turns out, you can certainly use stoichiometric, or you can use an equal amount. You could actually pre-make the enamine, but that wouldn't be catalytic, right? That would be sort of stoichiometric in a way. But it turns out that a lot of this type of chemistry that does this type of stuff, you can actually get away with lower equivalence again because you regenerate, right? You can imagine regenerating the carbonyl. And so what can often happen is you'll start with the ketone. Here, let me erase this and show you a catalytic cycle. Right, and so say, for example, you have start with, I'll put R group there, right? So if you start with, say, for example, this cyclic amine, right, what can happen, right, is that you take this and you treat it with that ketone, right? That's going to condense on the ketone. I guess I got the opposite side here. Right, so that's going to condense, so you sort of rotate it around to show it on the side of the nucleophile. Right, then what happens is you add, and this is all taking place in the same pot. You'll have, say, for example, your aldehyde. So if we give this R1, R1, R2, right, what's going to happen is chiral center there, stereogenic center. Now, say, for example, I make it with the steric control, so now that proton is coming towards you, right? And then what happens is in this process here, right, you generate water, right? And what can then happen is that water can then come back into this cycle. Hydrolyze the imine, right? Regenerate the amine, and your product, in this case, will be this component here. So again, that's the idea behind catalysis, right? Is that you have a reagent in there that drives the reaction that isn't necessarily consumed. And so this would be what we call catalytic cycle, yeah.
Yes, I understand that you used to make a specific enantiomer, so like for our purposes, now we're supposed to know which one to use.
Oh, no, yeah. Yeah, no. You wouldn't be able to draw, I wouldn't ask you to draw a transition state. I'm just trying to explain to you guys why enamine catalysis is important. Sure, you could use it. You could use it and say, I would pick the enantiomer that would lead to the pure product. Because you don't know, right? Because that's the thing, right? Oftentimes people do asymmetric catalysis and they don't know which enantiomer they're going to get. And after they do the chemistry, they subsequently try and figure it out. So in a case like imine catalysis, it's well known, and so you can predict because of people have studied it, but this isn't an asymmetric catalysis course. I just want you guys to be able to appreciate why enamine catalysis is important. Again, I think it's pretty standard that you could say, oh, any of these electrophiles that you treated with enolates, you could imagine doing with enamines. But this is, I think, one of the most important reasons why enamine catalysis is important. It's one of the reasons why I think enamine catalysis is important. And again, you guys can appreciate why stereochemistry is important. And so this is one of the, I think, cool ways in which people are able to do this. And there's a lot of cool stuff behind this, but this is just sort of the introduction kind of component to it. But yeah, when people do asymmetric catalysis, they don't know oftentimes. They'll sort of put an aspect of chirality in it and hope that that will then confer the chirality, and then they'll usually get 2 peaks, but they'll have no idea, like they'll have a readout, and their first readout will be in a chiral column, and they'll see the 2 peaks, and it'll be 1-to-1. And then as they're setting up their catalyst, they'll just hope that one peak goes down and the other peak goes up. And then subsequently, they'll generally try to characterize specifically what that enantiomer is. Sometimes it's not quite known. They'll have to make known molecules. Yeah.
Is there like a general percentage as to like the percent out of the times that they try to do it, the percentage that you'll get the purest one?
Oh yeah, no, it takes a long time. No, I mean people's complete. Yeah, I mean go read Stacy Brenner's work. I mean it's like papers, like years are published, just trying to develop one reaction that gives. Yeah, this is like an entire field. So anyway, so that's the point. Did somebody else have their hand raised? I don't want to spend too much time on this. I just sort of wanted to introduce you guys. I'm going to show you 2 things about enamine catalysis. Again, you guys can make those transitions. If you see an enamine, any of those electrophiles that we saw, you can imagine treating them too. Right? So it's not that, groundbreaking, right? It's like this is just another nucleophile. But I just want to show you the 2 examples. And again, you can imagine this type of stuff taking place with a variety of different electrophiles. So did I see a hand up? Did you have a hand up? Okay. All right, so this is one instance where when I think of enamine catalysis personally, and I think of why it's valuable, this is one of the things that always jumps out at me. And I think that, we really haven't discussed asymmetric chemistry that much. But this is a big deal. The other area where I think you'll see enamine, and you guys could probably perhaps appreciate, is in indoles. Okay, so indoles. Again, I know you guys all, like a lot of you guys at least, are big into medicine and pre-med and stuff. And so I forget what the number is. Anytime you hear a synthetic chemist talking about indole chemistry, they'll shoot some number that's kind of ridiculous. It's something like 60% of drugs. Maybe it's bigger. Maybe it's lower. I don't remember. But it's some very, very high percentage, surprisingly high percentage of drugs actually contain indoles in them. And so there's a lot of work that people do to try to think about how they can functionalize, for example, indoles. And if you look at the indole, right, certainly this is the way that we draw it. And again, we'll discuss indoles and how they're aromatic in a couple weeks. But you can clearly see that built within that, right, is that enamine. And so as you can imagine, taking these molecules and treating them with a variety of different electrophiles will actually react with these compounds, and they'll react in such a way where, as you might imagine, they're going to react at this position here, right? So, and the net result in this case, you actually redrive aromaticity, and so I'll discuss the mechanism really quickly. But you end up getting to electrophiles that look something like this. So you're able to substitute indoles fairly easily, simply because of that enamine within the compound. And so, again, as you would imagine, I'm sure you guys could all draw, you would get to something like right? And say, for example, if this electrophile has a, say, for example, if it's alkyl bromide or something like that, right? All right, so you can imagine that bromide will simply re-aromatize that system. Again, we'll talk about driving forces behind aromaticity and so forth, but this is one of those cases that we spoke of earlier. Sometimes you can go back to the ketone. In other instances, you can certainly go to the back to that sort of enamine. So again, I think when I think of enamine chemistry, it's really these 2 areas that I think are sort of worth it for you guys. And again, in part because chirality is something that you guys are all familiar with. You spent a lot of time learning RNS, learning all about why chirality is important, but we don't really spend too much time thinking about how and what the methods are that we can create chirality. And certainly enamine is one of the most well-known ways to sort of get that. This is the sort of hallmark of what we call organocatalysis, of doing asymmetric catalysis with organic molecules. There's a whole bunch of metal-based ways, but But then again, indole chemistry, I think, because indoles are so prevalent in drugs, you can imagine a synthesis problem that I could give you guys where I ask you guys to functionalize an indole, and this is the kind of thing that you would sort of do. Okay? So that's really all I wanted to discuss for enamines. Again, hopefully you see the sort of parallels between enamine catalysis and enolates. Hopefully you can sort of understand that and sort of appreciate that. I just want to make a couple more points about enolate chemistry, maybe spend the next 20 minutes to half hour talking about a few extensions of enolate chemistry. So I'll call this sort of enamine-like, or let's say enolate-like. Right, and so if we start to think about we just do a quick little sort of review, right? If we have a ketone, right, we have enolizable protons, right? We take this molecule and we can treat it with lithium disopropyl amide. Again, you don't have to just show this disopropyl amide. Right? We end up pushing them up into the oxygen, right? Because this is how it reacts. This is how the more stable resonance form, again, because you have the negative charge on that oxygen. But again, we discussed the reactivity of it and how it reacts more like the resonance form. Right? And so we saw this in a similar way, right, with enamine chemistry, right? This is kind of how it exists, and this is how it kind of reacts. You can think about it like this. But you'll notice some parallels here, right? It all has to do with the kind of oxidation state that we're dealing with at this position, right? It's sort of getting to these systems, right, where you have electrons, right, that can donate back into a double bond, right? So it's to draw a parallel to something that perhaps we've seen even earlier, right? You could sort of imagine similar systems, right? If we think about what we have here, much of the chemistry that we've seen in terms of nucleophiles, right? This sort of idea is that nucleophiles need to have lone pairs, right? And so oftentimes we'll think about the lone pairs as being what's attacking, right? And really all that these are, right, are lone pairs that are in conjugation to a double bond, right? This allows us, that's kind of how you could think about these, is it's lone pairs sort of in conjugation with this double bond, which provides a resonance form, right? And it's the resonance form that really displays the reactivity that's so analogous to what we had perhaps seen in other instances. In many ways, we could draw parallels, say, for example, to allyl, right? So you guys remember the term allyl group, right? An allyl group is one where you have CH2, CH, CH2 double bond, right? And again, depending upon how you run this chemistry, sometimes there can be interesting selectivity issue, right? You can imagine this carbon being the nucleophile, you can imagine this carbon being the nucleophile. The same the parallel way that we have there. So this is another example where you can imagine, right, a couple different products forming, and again, depending upon how you sort of react this, imagine two possible products, right, where it reacts. And so you may even be able to draw this parallel back even further to perhaps when we talk about allylation type chemistry. But again, you know, so this is just the parallel, right? It's lone pairs. That's what ties all of these together. It's lone pairs tied up within a carbonyl. And so there's many other instances where we can imagine, sorry, in this case carbonyl, I should say a double bond, right? A lone pair adjacent to pi orbitals, lone pair next to double bonds. And so there are many instances where you could imagine that you could have similar types of scenarios. One of them, right, and it's just the ability to perhaps generate these. One of these is sort of nitroalkane. Let me make sure I draw this as much of a parallel as I can. So here's a nitroalkane, right? And if this nitroalkane has these protons here, right, you can sort of see, as I've drawn this nitroalkane, right, is very analogous to, say, for example, the ketone, right? You've got your carbon with your methylene here, and adjacent to that is a pi system, right, a double bond, right? And so, as it turns out, instances like, in the same way that we think about enolates, this has, as you might imagine, a much lower pKa than your standard alkane, right? In this case, the pKa is about somewhere around 10. So you can actually deprotonate this with actually fairly mild bases, like sodium hydroxide, or say, for example, if you want to use LDA, you could, but say sodium hydroxide, right? And here again, right, what we can do is that exact same parallel reaction that we drew here, right? So that should look the same. Really all we've done is put a nitrogen, right, where that functional group is there. Right? And in this case, now what we have is this molecule here. So again, here's the parallel. Right? This is how it would perhaps want to exist, right? This is how this one will want to exist. But the way that it reacts is a little bit different, right? Same way as this one, same way as this one. There's this alternative resonance form, a little bit higher in energy. But again, this is the way that it will react. Okay, so in the case of, say, for example, a nitroalkane, if you wanted to take a nitroalkane and you wanted to treat it to a base, you could generate this very analogous nucleophile. And then what do you think you could do with it? Treat it with a ton of different... No, you don't want to treat it with an enolate. You want to treat it with an electrophile, right? So you take it and treat it with an electrophile. And again, that electrophile could be an aldehyde, it could be alkyl halide, it could be really, in principle, any of those electrophiles that we've seen in the past, right? So again, hopefully we're getting to the point where you guys could start, like, this might sound bizarre, but you guys could start thinking about your own reactions, right? Like I don't know that I want to do this reaction. Right? We haven't seen it in class yet, but I'd like to do this in a synthesis problem. It'll be really useful, right? It's fine. You make a nucleophile, you make an electrophile, that's a reaction. And there's any number of these that you could imagine that we could sort of do. And so if that electrophile is, say, an aldehyde, right, we're going to just add in, right? And we'll have the alkoxide, right? And what do we do at the end of the reaction? We work it up. So oftentimes we'll just draw this in the protonated form. Right? Now in this case, we've got a nitro group, right? And we may not really think of nitro groups as perhaps being all that useful, right? But have we learned? I don't know if we learned this or not yet. Do you guys know that you can reduce a nitro? Right? What is a nitro analogous to? It's kind of like a carboxylic acid, right? But it's it's kind of a carboxylic acid, but which has a nitrogen in it. And so it's this very high oxidation state, very carboxylic acid-like. And so not surprisingly, you can reduce these down. And it turns out that in these cases, you can reduce them down pretty easily, all the way down to the amine. And again, we'll learn about this a little bit more. Perhaps we'll talk about it more when we discuss, amine chemistry, but I'll just sort of tell you guys that if you take these molecules and you reduce it, in this case, it's a reduction condition, similar to reducing an alkane. But again, we see a lot of parallels here. What will happen is you'll get to the amine. Right? And so again, just from a synthetic standpoint, we discussed the value of amines in the past and how we can do different things with amines. But again, here's a nice way where if you see, say, for example, an amino alcohol, right, that we could perhaps begin to make important molecules, particularly in synthesis. Yes? Through to nitro? Imines is what you're thinking of. I have to check that out. I don't know if that would reduce in nitro. I have to double check that. I don't think that sodium borohydride would, but you might be able to coax it to under specific conditions, yeah.
If you the word that's in a safe environment, how is it oxygen stable?
That's a great point. This is the beauty of paper chemistry. So the question was just asked. So this is a known reaction. It's called a Henry reaction. And the question was asked, if this is worked up under acidic conditions, what else might happen under those acidic conditions? What are you thinking? Why are you saying, I don't like that? Oh, this! Oh, why is this not protonated? No, that's not going to be protonated.
I know it's not. Resonance makes it stable.
Well, the resonance makes it stable, but it's not just that. It's the overall species. You have this positively charged. This is not a full-blown alkoxide. This is not even a full-blown carboxylate, because what you have next to it is a positively charged nitrogen, and so it's stable. They're stable. Yeah, nitrous acid. What's the pK of nitric acid? I don't know. I have to look that up. But that would kind of be the analogy is nitric acid. But even in that case, yeah, I don't know. No, but it's not. Nitros are fine. I thought you were going to say something else. What else might happen here if you treat this with an acid? That's not going to happen, except under really strong leads. But it would have to be pretty strong. With like triplet acid, yeah. Magic super acid, yeah. Say that louder. Condensation chemistry, right? Where's that parallel coming from? Well, what kind of reaction is this similar to? What's this similar to? Right, and then alcohol condensation, right? And so that's 100% right. So that's where I thought you were going. So certainly you can imagine under the workup in the same way, again, that same parallel, if you treat this under acidic conditions, condensation, again, look up alcohol condensation, draw the parallel, and what could happen is, right, you could generate vinyl, right, you can actually do an elimination, right, so look up alcohol condensation and you should see the parallel. Again, what's going to happen here is you'll protonate here and you'll eliminate water, okay? So, with that, again, this is a reaction that actually has a name, not that you need it, but this is called a Henry reaction, so it's and again, from this standpoint, you can do a lot of different things. So these are versatile intermediates. We can take them to amino alcohol. We could take them to the vinyl nitro compound. Again, you have the alcohol there. You can imagine oxidizing that and taking to the ketone, right? You can imagine oxidizing to the ketone and then perhaps trying to selectively reduce the oxygen. Let me show you guys this. No, never mind. Better left for later on. Actually, I will, but I'll transition really quickly. We'll discuss this stuff a little bit later on, I think, in amine chemistry, but I think now is a good time to discuss this as well. Because we can draw these parallels in terms of the nucleophiles, and I bet you guys could actually start to come up with some of your own nucleophiles as well. What are some other, say, for example, functional groups that have, say, for example, some other alternative, what are other instances where you've seen sort of stuff double bonded to oxygen, right? That stabilizes different things to resonance. We were just talking to phosphorus, right? So you can imagine situations where, say, for example, phosphorus, right? If you have, say, for example, something like this, right? You have this methyl group here, right? You could imagine that you could begin to do chemistry with that. So somebody just created a reaction that they had never seen before. If I take this alkyl phosphate, right, I might be able to do chemistry where I generate some type of enolate there, right? What about sulfur, right? Sulfur, right? You can imagine situations where you have right? We can imagine situations where we have this compound here. Okay, well, we want to make this into an enolate-like compound. Well, you can imagine taking this and treating it to a base, right? In the same way, we'll get a stabilized enolate. So in many ways, right? And again, we can sort of build off these. Now, we really haven't seen sulfur or phosphorus too much in the reactions that we've done, other than perhaps as reagents that drive chemistry. But again, this is, again, you can sort of start to see these parallels, and the point here isn't to throw more reactions onto your plate, but simply to recognize, I hope that you guys can start to recognize, hopefully, why these molecules are valuable. And why do you think these reactions are valuable? What's so nice about them? Yeah. Yeah, we're making carbon to carbon bonds. And we're actually being able to generate the nucleophile, right, without having to do super crazy chemistry, right? We think about our standard, well, I don't want to call Grignard, say, for example, super crazy chemistry, but it doesn't require, say, for example, having a halogen there that a Grignard would, say, right? So there are instances where you can make that lithium, right, that lithium-based anion, right, or sodium-based anion simply by deprotonating. So that's, I think, the parallel that these all have is that they have lower pKa values, so you can deprotonate them, similar to acetylene, right? That was one of the big things about acetylene, right, and why acetylene was so valuable. You can deprotonate acetylene with sodium amide or something like that. You don't have to have a halogen there or anything like that. You can simply do acid-base chemistry to generate the new nucleophile, and that's the same here, yeah. Yeah, I mean, it's going to depend. I would assume that a Grignard would be more reactive just because it doesn't have a stabilized charge. But there could be instances where it's kind of an irrelevant question in many ways. Because it's like we want our nucleophiles and we want at least for this course I would say, unless you're trying to do like 5 reactions in a single pot and you've mixed everything together and you're hoping that the Grignard's going to react first and generate an enolate, which will then react second or something like that, setting off the cascade process. So it's a good question, but I think it's one that's a little bit irrelevant. I think the more important point is what has most of this organic chemistry course been? It's been identify a nucleophile, identify an electrophile, and they react to make bonds. And really what this enolate chapter has been is here's a new class of nucleophiles, and hopefully what I'm showing you guys here is that there are a lot of other potential groups. Yeah?
I think the next question, it seems like the enolate is more reactive than Grignard, just because it acts in substitution reactions, while Grignard only acts like a carbon or an oxide.
Well, so you were asking different questions. You're asking how versatile, not more reactive. Certainly a Grignard is a stronger nucleophile. But stronger and better, I think, is, you could imagine certain mechanisms within enolate chemistry where, say, for example, with an aldehyde, you can have 6-member transition states that might lower the energy barrier. But yeah, there's no doubt a Grignard is stronger. Just think about the pKa, right? Because there's parallels that could be drawn. In Enolate, you can deprotonate easier. You can't deprotonate, say, for example, a methyl Grignard. So stronger versus more versatile is, I think, the difference. And I think what that's getting to, and perhaps what you're getting to, is when you're saying better, not stronger, a better nucleophile, perhaps because versatility. Yeah, no. It's probably because the Grignard could also behave as a base.
I have another question.
Yes.
It talks about reducing like the alkene in the conjugated system. I use H2 rhodium, I can use something like that. I didn't understand it. So it seems like we go after that double bond acts more than electrified than a nucleophile.
So you can reduce, yeah, you can reduce those with, there's a hydride source that's called superhydride that you can actually, so chemists have been pretty good at taking advantage of all these different things. So in a case like,
But it doesn't seem like you use hydride. You're using H2. You're acting as
so hold on. So two things. I think you're getting at lots of things here. So first of all, if you've got an enone, so the question that was asked is if you want to, say, for example, reduce an enone. Again, we saw that, say, for example, if you take this and you treat it with LAH, it'll go under here, and this might come down to what you're asking, whereas if you take this and treat it with, say, for example, rhodium and hydrogen, which is complete BS. Like, they're just giving you random reagents. In truth, maybe that's the case, but it's like, there are so many different metal catalysts out there that generally you find reactions similar enough to yours, and you just use that metal that they've used. And so simply to say rhodium, there's tons of different types of rhodium, right? It's not like, there's different oxidation states of rhodium, there's different ligands for rhodium, there's different. So when the book says rhodium and hydrogen will do this, and nickel and hydrogen will do this, there's something to that probably, but from my standpoint, it's kind of silly because to memorize the different metals. The point is that the metal can do one thing, and a different metal can do the other. So, but to answer your second question, I think it's that you're kind of saying, well, there's two delta positives here, right? There's delta positive on the carbonyl, and there's a delta positive at the beta position. And we discussed this a little bit in class, at least in terms of nucleophiles, and how, again, I didn't want to get too much into it, but this sort of idea of where, and again, this gets down to more physical organic. We won't discuss this perhaps when I discuss dienes, which maybe today. We'll start to understand it a little bit more. But the general idea here is that conjugated systems don't exist as an alkene and a carbonyl. They exist all together. It's a fully conjugated pi system. And there are LUMOs and HOMOs that are associated with these, where those sort of electrons lie within that overall process. And it just so happens, for reasons that are beyond the scope of this course, that the LUMO in this system is at this position here. And so in general, anytime you treat this with a nucleophile, it's going to add here. The difference is that when you have charged nucleophiles, because the biggest buildup of positive charge is here. And so when you have electrostatic interactions, it can actually drive it to go the other way. Beyond that, you're asking about hydrogenation, but it's still an alkene, so there's just ways that you can hydrogenate that. But there's also ways that you can add hydride nucleophiles in. In fact, if you want to hydrogenate this and you actually try to do it with lithium aluminum hydride, that wouldn't be the go-to condition. The go-to conditions would be things called Lusch reduction conditions, which is like cerium trichloride and methanol with sodium borohydride or something like that. It's not in your book. But that's the conditions that people have worked out to selectively go after this. If you want to go to the beta conditions, truthfully, you're not going to probably use rhodium and hydrogen because you'd be nervous it's going to reduce this. The go-to conditions are going to be this reagent called superhydride, which is a boron hydride reagent. So take everything that the book says with a certain level of, you could drive you crazy. The important part is you can select over this and you can select over this. Okay. All right. Other questions? All right. If anybody wants to use Lusch reduction on their exam in a synthesis problem, you get bonus points. Write that down. All right, so okay. So we talk about how these can all be sort of new nucleophiles we can generate, and again, I think when I think about the versatility, then I think about the ability of these to be generated. That's largely what it comes down to, is that you can deprotonate them to make new nucleophiles. And thus they simply exist in my mind as another class. Whether they do elimination, whether they do substitution, whether they may have these side products that perhaps are being brought up here that go back to this, is this a good acid, is this a good base? I mean, the truth of the matter is that when I was in grad school, we spent forever trying to get a nucleophilic substitution to take place that kept doing elimination. So you recognize that they can do both, and you do your best to try to overcome it. But so the more important point is to recognize that those all have the potential as nucleophiles, and certainly I would argue that there would be a way around it, and if there's nothing in the literature to find a way around it, you can generally work your way around it. Now, I don't remember if we discussed imines too much, right? But I think as some of you brought up, we can also draw parallels to things such as the electrophiles, right? So we spent a lot of time discussing carbonyls as being electrophiles. And we did discuss, to an extent, imines being good electrophiles as well, specifically within the context of, I think, reduction, right? We discussed the sodium cyanoborohydride, which is, I think, what might have been coming up before when we were discussing these two. So certainly this is a reagent that you can also, for example, use as a sort of electrophile as well. And so one reaction I thought would be kind of interesting to discuss, we can sort of think about the mechanism behind this, is a pretty interesting reaction where if you take this molecule and you treat it with a cyanide source, okay, and then your subsequent step is to do acid, aqueous acid, let me ask you a question. If you guys could sort of predict what would happen in this reaction, what do you guys think would happen in that first step, right? This is a nucleophile. This is an electrophile. What's going to happen? It's going to attack this guy. Right? And so this is the first step in this reaction, following a sort of workup. I'll just show it in protonate form. And now, based upon what we've also learned, what do you guys think would happen if I took this molecule and I treated it to acid and water? Where? Right. This is going to hydrolyze the carboxylic acid. And again, you guys should be able to draw the mechanism of this, but you recognize that cyanide is the same oxidation state as the carboxylic acid. Anybody know what that molecule is? No, I thought this was the last one. So anyway, so you guys can see this is a pretty cool process. You can actually do that people use quite a bit to generate, say, for example, non-native amino acids. As you can imagine, if you're going to generate amino acids, you might want to make a chiral too. So people have generated some cool ways to make that. At least in that track. Okay, so I think that's going to be it for enolate chemistry. And I think what I'll spend the remainder part of the course doing, we're going to get into some chemistry. Part of the reason why I've been moving fast is that there's going to be some stuff coming up that I think requires a lot of practice. So as you guys know, if you don't know, now you know. I'm very big on mechanisms. I'm very big on synthesis. I'm a synthetic organic chemist. So these are the things that I try to teach you guys, and I think it gives a lot of problem solving. What we haven't discussed too much to date is a few more sort of molecular orbital, physical organic chemistry-based things. So we'll discuss that a little bit. I think Diene chemistry, which is the sort of next progression to the course, is one of the things that can introduce us to them. But there's also some chemistry within dienes, specifically two classes of reactions that I think allow us to start thinking about stereochemistry a little bit more again. So we've discussed asymmetric chemistry, but for the most part of this course, we haven't really discussed we haven't discussed diastereoselectivity, right? And I think it's one of those things I think is good practice. I think it helps you visualize how molecules behave in sort of three-dimensional space on paper, and really work on that skill to actually visualize how the molecules are coming together in a specific orientation and how that leads to a specific stereoisomer. And certainly those are things that I think can provide issues. I'm sure you know how much you guys struggled just figuring out whether something was R or S. You know, once you start making multiple bonds simultaneously in lots of different rings, you can imagine the increase in that. So I want to sort of get to some of that stuff so that we can start to think about stereochemistry within these types of more complex and powerful, I think, reactions. And so I think we'll go ahead and get started. But today I'll sort of introduce dienes and perhaps get to some of these reactions and maybe get you guys thinking, and we can discuss more in depth about this stuff next week. Okay, so a couple things about dienes. Right, dienes can come in a couple different forms, right? We can have, I mean, what is a diene but a molecule that has two alkenes, right? And so obviously two alkenes can be anywhere in a molecule. And largely throughout the course today, we'll be talking about the two reactions that I'm going to really stress involve one of them, which is conjugated dienes. Right, and that's when we have alkenes that are sort of connected. So we have two pi systems together, or unconjugated dienes, or non-conjugated, however you want to call it. Okay. So unconjugated dienes. What I'm talking about, unconjugated dienes, is when there's some type of spacer in between them. So if they're separated by, say for example, an atom, a nitrogen, something that doesn't allow these to sort of take place. And there's big chemistry-based differences between these two types of dienes, as you can imagine. And it really starts with, I think, one way to at least think about this, just to get you sort of thinking about the differences of these two, is that if I were to ask you, in a quiz, say for example, here's two dienes, and I'm going to treat these to, say for example, acid, which one of these two dienes would sort of react faster? And I'm hearing a bunch of people say, heard some people say the unconjugated, I heard some people say the conjugated. And I think that an argument might be able to be made for either. For the people that said unconjugated, somebody said unconjugated. Yeah, so I had one person say unconjugated. They said that this would probably react slower. Why do you think it would react slower? Sorry, why would the unconjugated react faster?
Because if you take off the hydrogen with an acid, you get rid
So okay, hold on. I think you meant the opposite. Yeah. So the idea here is that you can react either of these with an acid. Again, there's two sites that we could protonate, right? But as I'm sure you guys could all tell me by this point in your organic chemistry careers, it's gonna lead to that proton. Proton's gonna end up there, right? And there's, you could have probably known this even without appreciating the resonance form, right? Just based upon thinking about Markov-Nikov addition of water across an alkene. But certainly in these cases, it's even better, right? Because of the fact that you have that resonance form, right? You can stabilize this molecule through resonance. Whereas in the case of the unconjugated dienes, you're not going to have that, right? If you People will try to, so maybe it's worth me just drawing it, because I see people try to draw these resonance forms through Dienes, but it's again, I think, important to recognize that when you have a spacer in between, right, there's no resonance form that you can draw there. You could try to draw a resonance form, right, but then you're going to sort of make this ring, for example, right, so that becomes a reaction in a way. It's not really a resonance form. I guess you could kind of consider it a resonance form, but again, it's certainly not in the case of the sort of conjugated system. And so you can see that there's this inherent conjugated system. So anybody want to make an argument that, aside from this, that perhaps this would be slower to react? Yeah.
Well, I guess you're breaking the conjugation.
Yeah. Yeah. So that would have been the argument that I think you would have made in the other cases, that conjugation is a stabilizing factor, and you're breaking that conjugation. Yeah.
But if you're breaking them, I don't bring a sigma bond. Like if you're breaking the conjugation.
Yeah, but you're comparing. You're comparing across these two, and the idea would be that yeah. But I think the fact that you've got a more stabilized cation trumps it. But there could be that argument that could be made. So good. Thank you for that. And again, this may come into play more in terms of breaking conjugation, specifically when we talk about aromatic compounds, where perhaps there's an even bigger penalty paid by breaking that conjugation in even more stabilized systems. So oftentimes when we think about, so there's a couple of aspects that I want to discuss about dienes. The first is that we'll focus on conjugated dienes, but again, you can start to see it right away. The fact that you have this conjugated system here sort of bears out in at least something that we've seen in the past, right? Resonance forms. But if we think about this sort of overall system, when you have sort of two double bonds next to each other, what you sort of recognize is that you now have a network of p orbitals, right? And so what can often happen in these cases is that the molecule, because again, we've discussed in the past how electrons are kind of claustrophobic in nature. If they can sort of spread themselves out over more space, that's something that makes them happy. If we want to personify atoms and electrons. But in this case, right, what we have is this ability to really flow directly throughout that entire sort of system of four sort of pi orbitals. And so again, that becomes a stabilizing factor, which is what was brought up earlier about it liking that, right? And if it has that and you break its ability to have that, then perhaps it might not be that happy. But again, the sort of resonance of the protonation is going to trump it, but in instances of aromaticity, we'll see this in the past. But anyway, the sort of net result of this is that we now have a completely new type of really network of electrons that we really haven't seen before. And so there's some certain elements of understanding them that require us to look at them perhaps a little bit differently than we have in the past. And so oftentimes when we look at dienes, we don't think about the dienes as two double bonds. We look at them as a collection of the four p orbitals together, and thus the chemistry, as we'll see as we move forward, there's some specific chemistry that can be dictated and can be explained based upon some of the principles of sort of what we can call, I guess, valence orbital theory, if we want to sort of think about it at that level. And so we begin to start thinking about these molecular orbitals in a way. Now, again, I'm not a physical organic chemist, and I won't be able to even do justice trying to get too deep into the physical organic chemistry aspect of this. But what I will try to sort of teach you guys is how we as organic chemists can begin to think about how the orbitals play and exist at the most important areas of reactions, right? And when we think about any reaction taking place, oftentimes we're thinking about the HOMO, right? You guys have heard this in the past, and the LUMO, right? The highest occupied electrons, so there's a lot of electrons in a species, right? Whatever have the most energy, right, are going to be the most likely to react. Conversely, where the electrons are going to go on the electrophilic component, right, are those aspects of the species, right, in which case it doesn't have electrons, right, but we want the lowest energy of those electrons, right? And so as we'll see, when you fill up, say for example, any molecular orbital per se, you sort of will often identify where the HOMO is, and you'll identify where the LUMO is, and sometimes these can help us explain certain types of chemistry. Okay? Now, I'll give my sort of, for lack of better sort of term, I guess, very superficial view of how I think about these molecular orbitals. Okay. Now, there's a lot of math behind orbitals, but what I can tell you is that when you start thinking about the energetics of these systems, we can sort of equate them to sort of wave function theory type systems. And so we can start to think about, you know, when something has a big wave, right, that's sort of low in energy, right, and when something's got a lot of things, right, that's really high in energy. This is kind of very superficial physics on my part. But we've seen this sort of thinking about wave functions in the past. And so this is generally your lower in energy, this is kind of your higher in energy. And so as the electrons flow within these systems, we can think about a similar type of process, right? And so within this sort of wave function here, we have a system where at the lowest energy, right, we actually have a wave that kind of fills the overall whole system here. And so we'll often fill this where we're all positive, right? Everything is sort of in the positive direction. It's sort of arcing over the whole system, right? And as we move up, right, we begin to have these additional nodes. And so as we move up to the second level, right, we're going to have the sort of halfway point in this, and that is a wave function whereby sort of half of this is in the positive and half of it is in the negative. And so from an organic chemist standpoint, we'll start to fill this up here, and these guys down here, okay? And we can keep moving on this. Once we get a little bit further along, like where this sort of starts and finishes can sort of change, but again, we have oftentimes what we'll discuss is this is what we'll call a node. So we'll say no nodes, one node, and then up here we're going to have two nodes. And depending upon where we put those two nodes, they can be a few different sort of locations, but they has to be symmetric in some way. And so what I'll do is I'll put them there and there, okay? Down, down, up. Okay, and so in this case we have the sort of two nodes, okay? What you'll notice as we're sort of going up is that the sort of external points and oftentimes the internal points will sort of switch, right? So on the external, both of these are in the same direction. They're on different directions, but the same direction. And there's, again, one more that we can have, right, where we have now three nodes. Right, because in this case it's kind of like that. In this case it's down, up, down, right? And again, so now we have three nodes, okay? And we can't go more than three nodes in the system, right? So this is going to be the highest energy. So we go from no nodes, right, where they're all on the same axis, this is the lowest energy. And again, we can just sort of think about our very general knowledge based upon sort of waves and things about energetics of different waves. And the top one is going to be the highest energy in terms of that component. Now, as we fill this orbital, we can begin to start putting electrons into each of these different orbitals, and we fill them up much the same way that you guys have filled up, perhaps. Do you guys do molecular orbital theory much in like maybe Gen Chem a little bit? Right? So you kind of fill them up oftentimes two in a row, two at a time, right? So we can kind of do the same thing here. We pair them up. So we're not going to fill them all up. We'd like to have them in pairs. So two electrons will go into the lowest orbital. The next two will go in here. And the fact of the matter is that's all we have, right? Is we've got 4 electrons in the system, and so at this point we're done, right? And so this becomes our highest occupied molecular orbital. That becomes our highest occupied molecular orbital, right? And this one up here becomes our lowest occupied. Thank you. Unoccupied. Right, so HOMO and LUMO, right? And so as we just start to discuss chemistry, again, we've got about 10 minutes left. As we begin to discuss a lot of the chemistry within dienes, we'll begin to sort of think about it within this sort of confines. And really, I'm sort of setting this up, but it's really to explain one reaction. But there's a lot of reactions that can actually be explained why they work through this process. But we'll discuss them a little bit. So I want to do one more molecular orbital for one more component, and that's going to be the alkene, a single alkene. And so the single alkene, again, we discussed the dienes, right, and how that would exist. And so, but we can also do it with the alkene as well, right? In this case, we have 2 electrons. But we can do the same type of thing that we just did here, right? We have, in this case, we're only going to have the maximum of 1 node, right? So we have either no node or 1 node, right? And again, in this case, we're going to fill them up, but this only has 2 electrons. So now this, right, becomes our HOMO, and this becomes our LUMO, okay? Now, we're going to discuss a reaction. I'll sort of introduce it now, and we'll discuss it. We'll get more into stereochemistry, but I just think that this was a good time, given the time that we had to introduce Diels-Alder chemistry. But one of the cool reactions that we're sort of going to learn is this reaction known as the Diels-Alder reaction. And formally, what this is a reaction whereby we actually make a couple of different carbon-carbon bonds at the same time. It's a pretty powerful, very, very powerful reaction. Okay? And the question becomes, why does this reaction work? How people are ahead in the reading. So I want to go through this a little bit slower. I know that some of you guys have read this, but I kind of want to introduce this because I think it's an interesting concept. It's kind of fascinating. In this case, we have really 2 reacting intermediates. And in the past, we've discussed a lot of things in terms of nucleophiles and electrophiles, right? Electrons are going to go from where they are to where they want to be, right? And so in the same way, when we're sort of thinking about Diels-Alder chemistry, one of these, right, it doesn't really matter which one, right? One of them, we have sort of electron demand and inverse electron demand Diels-Alder, but we'll discuss that in a little bit. But again, in one case, we're going to have one of them is either going to be the electrophile or the nucleophile, and the other one will just be the opposite, right? And so again, it doesn't really matter which one we sort of pick, but at some point what we're going to need to take place is the highest occupied. One will effectively be our nucleophile, which will be the HOMO, and the other one will be our LUMO, or vice versa, right? Or this could be our HOMO and this could be our LUMO, right? But what's interesting about this is that when we start to think about, say, for example, this wave function that I've sort of illustrated here, right? Let's do the classic Diels-Alder. So generally, when we think about Diels-Alders, we think about electronically poor alkenes. So we think about these being the electrophiles and these being the nucleophiles, but you can flip-flop them. So we'll take the highest occupied molecular orbital here, and we'll take the lowest occupied unoccupied molecular orbital here. Right? And let's look at that wave function right there. Right? And so this is the HOMO, and this is the LUMO. Right? Now in the LUMO, what's going to happen? Right? We're going to be up high here and down low there. And what do you guys notice in this? Right? You sort of have, we could sort of draw this closer, what you see is you almost have this wave function continuing throughout the whole ring system, right? It starts up here, it goes down here, and it continues back up, and then down, and back up. Right? Do you guys see that? Right? And so this, effectively what happens is when you're doing this Diels-Alder reaction, this sort of wave function that I just explained over here actually is carried out throughout this 6-member transition state, right? I can't draw it sort of close, but this sort of explains how when you bring these close together, you almost continue this tie system, forming this bond, okay? Now, when you start to think about this is a cool reaction, right? It's cool. That's pretty cool. And it's powerful. But you can actually start to explain a lot of other chemistry in this as well, right? A Diels-Alder reaction can take place, right? But what about, say, for example, we can take this to the next level, and then I'll let you guys go. Let's talk about a 2 plus 2, right? A 2 plus 2 won't work, right? Right? This is, generally, it's not going to work. Why? Because, well, not because of ring strain, but because the HOMO and the LUMO, right? The HOMO of one has to react with the LUMO of the other. Well, let's look at that. Right? We've got this sort of wave function up here of the HOMO. We've got the sort of wave function over here of the LUMO. This matches, right? This doesn't. Right? So you can't have that same process that we had over here. Now here's the next question, right? You can do this reaction, but you need to do something a little bit different, right? If the HOMO, if the HOMO as exists here and the LUMO as exists over here aren't reacting with one another, what do you got to do? You got to change the HOMO or change the LUMO, right? But it turns out that one of the things that we can actually do is we can do this. But what we need to do is we need to shine light on this. And the reason is, in this case, the HOMO's here. Have you guys done much photochemistry? Probably not. Right? But when you excite systems, what can sometimes happen? Yeah, right? The electrons jump to a higher state. Right? So, and it doesn't do it uniformly. It doesn't do it across all the molecules, right? But what can happen is maybe 2% of the molecules will get excited at any given one time. So the majority of the molecules sort of exist with this molecular orbital diagram. But in the excited state, right, we have when we shine light on this, one of the molecules that's here goes into an excited state. So now, this is the HOMO. Right? So now we got a new HOMO. And now our HOMO looks like this. And now they match up and they can work. So looking at orbital theories and sort of thinking about pi bonds and thinking about it at this level, again, I don't completely understand it myself. I'm not a physical chemist, and I haven't invested the time in really thinking about it. But I think you can appreciate it for sure, and you can sort of use this at least as a guideline to explain a lot of the sort of chemistry that you see. And I think the 4 plus 2 versus the 2 plus 2. We'll talk about Diels-Alder a lot more. We'll spend probably an entire class on Diels-Alder chemistry, but I thought I would introduce it now at the time. So, all right, guys, I'll see you on Monday. Yeah.